This is Team 24081. The project is Oxygen on a Lunar Surface by Toby Adigan, Rachel Amlin, Julian Duff, and Gage Duncan. And the sponsor is University of Arizona, and our mentor is Dr. Farhang Shadman. As space exploration becomes more prominent, the challenges that we face in sustaining missions becomes more complex. The challenge at hand is exorbitant costs of providing oxygen for current and future space missions, with a staggering price tag of $102 million per kilogram of oxygen that is sent to space. Now, with NASA strategically planning crewed missions to explore Mars, the Moon, and asteroids, the need for cost-effective solutions becomes even more critical, especially considering the extended durations astronauts will spend in these challenging environments. This issue is of utmost importance because optimizing mission expenses is vital for the success of ongoing and upcoming space ventures. One promising solution to the costly oxygen supply challenge is leveraging in situ resource utilization, which is tapping into local resources like the lunar regolith on the moon. This lunar soil contains minerals rich in metal oxides, which make it an ideal candidate for oxygen extraction. Various methods such as hydrogen reduction, carbothermal reduction, and molten oxide electrolysis have been explored for this purpose. However, for our purpose of this project, we are utilizing a hydrogen reduction reaction to extract oxygen from the lunar regolith. By effectively recycling hydrogen, this method aims to reduce reliance on Earth's resupplies, enabling sustained lunar settlements and long-term crewed interstellar exploration. These innovations hold the potential to propel humanity towards deep space exploration goals and the establishment of a multiplanetary civilization. So, to overcome the high cost of oxygen supply in space missions, we can harness local resources like the lunar regolith through innovative extraction techniques. If this is successful, we can overcome these hurdles and embark on a journey of boundless exploration and discovery in space.
In order to extract oxygen from lunar regolith, there are three widely cited reaction methods. The first and least favorable of the three reaction methods was molten salt electrolysis. It required heating the regolith to the highest temperatures and also using a potential difference across the regolith, which demanded the most energy for the process. It also can lead to corrosion due to the molten salt, which leads to very low reactor lifetimes. Carbothermal reduction was the second potential reaction mechanism, which involved contacting methane over a bed of regolith. This operated at high temperatures and had undesirable side reactions. The final reaction method was hydrogen reduction. We selected this method because it is the most endorsed by scientists and engineers, operating at a low temperature and involving a simple scheme that prevents the loss of reactant. Hydrothermal reduction is traditionally studied as a benchtop reaction scheme, but this is not appropriate for scaling up our reaction for a potential moon colony. So we designed a fluidized bed reactor using the Cooney-Levenspiel bubbling bed model. So traditionally, hydrothermal reaction is studied at the benchtop scale, which is not appropriate for a potential lunar colony or scaling up our process. So we opted to employ a fluidized bed reactor using the Cooney and Levenspiel fluidized bed bubbling bed model and MATLAB simulation software. So the fluidized bed model meant that we would bubble all hydrogen through a volume of regolith through the bottom in order to achieve lift of the regolith particles and fluidize them throughout the bed to achieve a faster reaction time, which we found to be at least 5 times faster than those methods cited in literature at the benchtop scale. This process was advantageous because it allowed for greater mixing and lowered mass transfer limitations that would lower our reaction rates and other kinds of setups. And in addition, because of the lunar environment, very low gas velocities were required to achieve lift of our particles, which led to lower compressor and pumping duties than otherwise would be required on Earth. Using our fluidized bed model, created via MATLAB code, we were able to simulate flexible operating ranges of key reaction parameters, including performing optimization for variables such as temperature, which affected our rate constant via the Arrhenius equation, pressure, which affected our concentration of the hydrogen via the ideal gas law, and also parameters such as the volume and dimension of the reactor and the volumetric flow rate of the inlet hydrogen gas, which is only sufficient to be set between the minimum fluidization of the particles inside the bed and the maximum operating velocity, which is the particle terminal velocity, which will lead to the entrainment of the particle in the flow, carrying it outside of the bed.
In designing our lunar-based energy system, sustainability was paramount. We innovatively harnessed the high temperature of the reactor utilizing a cross-exchanger that leverages the exiting water at around 1,000 degrees Celsius. This water preheats the hydrogen stream to approximately 850 degrees Celsius before it enters the reactor, minimizing our reliance on external energy sources like solar panels or nuclear reactors. This method not only conserves energy but also lowers the water temperature, significantly reducing the load on our condenser. Addressing the moon's extreme temperature fluctuations, which range from 150 degrees to negative 150 degrees Celsius, posed a unique challenge. Our solution? We took advantage of the more stable temperature just below the lunar surface, about 50 degrees Celsius below zero, by burying coolant pipes. These pipes play a crucial role in our condenser system, efficiently condensing water while also facilitating the separation of hydrogen, which is then recycled back into our process. After condensation, the water undergoes electrolysis, splitting hydrogen and oxygen gases, which are stored in tanks using compressors. To ensure purity and maximize efficiency, all recovered hydrogen passes through a pressure swing absorption unit, which eliminates any excess water and impurities. This closed-loop system allows for longevity of our system on the moon without having to recharge with more hydrogen.
So as for the results of our process, per modular reaction, we're looking at creating about 40 grams of oxygen. Now, the average human does require about 840 grams of oxygen per day to survive. However, multiple modular reactions can be implemented depending on the requirements of the excavation. Overall, the implementation of hydrogen reduction to extract oxygen from the excessive amounts of lunar regolith present on the moon will yield to several positive impacts of space excavation. Those include longer exploration and/or rover missions, a reduced number of oxygen required at launch to bring to the moon, and finally, just the increased development of sustainable energy and technologies on the